Hey guys, let's get into some actual distance learning. So this unit we're going to be talking about exponential and logarithmic functions, and in this section we're first going to talk about just exponential functions. So before we start actually talking about the functions themselves, we're going to take a look at those exponent rules that you learned back in Algebra 1. So first of all, one thing I want you to notice is each of these rules has an a as the base. And that's because with each of these, we're assuming that the base is going to be the same for each one. So if things have different bases, we can't combine them together with their exponents. When we are multiplying their bases, we're going to add those exponents together. So if you have x to the third times x squared, well, if you have x times x times x, and then x times x together, that's x to the fifth. So that's why that one happens. When we're dividing, we subtract our exponents. So what I tend to do is I think about them kind of drawn out. If I have two x's on top and three x's on the bottom, and those two x's cancel out, I'm left with one x on the bottom. So that's the way I like to do it, but everybody has a different style. A negative exponent goes to wherever it isn't. So if your negative exponent is on top, it's going to go to the bottom like it is right here. If your negative exponent is on the bottom, it's going to come up to the top and become positive. This one comes up a whole lot in calculus. So what you might be wondering, why do I have to know all these rules? We did this in Algebra 1. Is it really going to come up that much? For me, no, but when it gets to be calculus, knowing this rule and this rule will make your life a whole heck of a lot easier. So with this guy, your root is the one that goes on the bottom. So if you have the square root, that's the same thing as something being taken to the 1/2 power. And then this exponent out here just remains an exponent. So whatever your power is goes on top of the fraction. Whatever your root is goes on the bottom of the fraction. When you take a power to a power, you multiply the powers. And anything to the 0 power is 1. So that's just helpful to know. Just some notation, just so we know. Earlier I talked about the base is always the same. It's always a. Base is that number that you're taking to a power. And that power is called your exponent. So that we would call 2 to the 4th power. Now we want to go through and write all of these as a single exponent. So here's the first thing I would do on A. We've got a 2 on top and we've got a 2 on the bottom. Those 2's will divide away. Then I have x to the 4th and x to the 3rd on top. When I put those together, 4 x's, 3 x's together, that makes 7. So I'll have x to the 7th. And that's still over x to the negative 2nd. So now we have a negative exponent, and negative exponents are bad. We want to make it positive. So what we're going to do is we're going to move that guy up to the top, and it'll make him positive. So now we'll have x to the 7th times x to the 2nd. So now we've got 7 x's on this side, and then another 2 x's altogether makes 9. So we'll end up with x to the 9th. Ooh, this next one is a booger. So it's kind of hard to see, but that is a negative 3 power. That's a squared right there. That negative 3 is going to go to everything. Actually, let's combine what's on the inside first. Let's do that. Let's combine what's on the inside first. So I'm going to keep that 2x squared up on top. Then we'll take 3 times 6, that's 18. And then x squared times x to the negative 4th gives me x to the negative 2nd. And that's to the negative 3rd power. So now what we want to do is we want to go through and distribute that negative third power to everything in that set of parentheses. So we still have our 2x squared up here on top. Uh-oh. Oh, it's because there's nothing there. That's why you can't see it. Okay. Over, and now 18 is to the negative third power. And x is to the positive sixth power, since we have to multiply our powers. So 18 is to the negative third power. That's a sad power. He's negative. So we need to make him positive and move him to the top. The way we're going to do that, we need to make him positive, so we move him to the top. Period. Done. So now I have 18 to the positive third power, 2x squared, over x to the sixth. So now what I like to do from here is I like to visualize it. So I have x times x on top, and then I have x multiplied by itself 6 times down there on the bottom. So 2 of those x's will cancel out. So that means I'm left with 4 x's on the bottom. So I still have 18 cubed times 2, and then I have x to the fourth in the denominator. All right, on this next one, let's start knocking stuff out. So I have 2 times x to the 0 power. Well, anything to the 0 power is 1. So right now I have 2 times 1. And then that whole thing gets cubed, so I just end up with 2 cubed. Over. And then that's an x to the fourth, x to the negative ninth. So when I combine the, first I'm going to put this as 2 to the first, just because these two 2's, those are the same bases. So that way I can think about exponents when it comes to my 2's as well, instead of just with variables. Now remember, in the denominator, those 2 x's, when I'm multiplying their bases, that means I have to add their exponents. So I'll end up with x to the negative fifth right there on that guy. So I can cancel some things out. I have 3 2's on top and only 1 2 on the bottom. So one of those 2's will cancel away. So we're just left with 2 to the second power. And then x is to the negative fifth down there. So to make him positive, we have to bring him up to the top. And then I'll have a positive x to the fifth. Okay, on to exponential functions. So, this is timely with what we're going through right now. So a lot of times exponential functions, if we're modeling a real world situation, the number we have multiplied we are multiplying our base by out front, that's our initial value. So however many we started with in the first place. B will be the base will be our growth or our decay rate, and then x is always our exponent. So if their base is bigger than 1, that means that's exponential growth. So exponential growth could be population, savings accounts, or something like how a virus spreads, or something like that. If your base is between 0 and 1, oh hello peanut, then it is radioactive decay. And radioactive decay, or I'm sorry, that's exponential decay. And exponential decay occurs in radioactive decay, like different substances that, radioactive substances, things like that. Okay, I gotta teach now. Okay, little kitten. Okay, kitten. All right, so now we're gonna graph and analyze 2 to the x power. So here we go. I want to go ahead and plug in -3, -2, -1, 0, 1, 2, and 3. So I'm going to start at 0. We know anything to the 0 power is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. All right. Now, remember, those negative exponents made it go to the bottom. So now when I have 2 to the negative first, now I have 1 over 2 to the first. So that's a half. 2 to the negative second, now I have 1 over 2 squared. So that's 1/4. Same idea with taking it to the negative third power, that's 1/8. If you notice, there's no power that I can take this to that will make it negative. Even if I make a really negative exponent, it's just going to make a tiny little number, but it's never going to go negative. So, here, let's start graphing this guy. So, at -3, I'm at an eighth. -2, I'm at a fourth. Half. 1, 2, 4, 8. All right, there we go. I did my best. Looks good enough to me. So for our domain here, we can go anywhere from left to right inside of there. So that's going to be from -infinity to +infinity. Now, just a second ago, we talked about how my graph will never be able to get below this x-axis. And actually, there's no way for me to take 2 to a power to get 0. Because remember, anything to the 0 power is 1. So I have an asymptote right here at y = 0. An asymptote at y = 0. So my range, remember my range is my y values. We always need to go from the bottom to the top. So the lowest my graph can go is 0. But because there's an asymptote there, my graph doesn't actually touch it. So that means I have to have parentheses on my 0. And then my graph goes straight up, so my function is going to approach infinity. And right here, this y-intercept right here is going to be at 0, 1. Now let's have a look at that end behavior. So as x approaches -infinity, so when x gets smaller and smaller and smaller and smaller and smaller, we were talking earlier about what happens when I take this to a really big negative power. That's just going to make it get closer and closer to 0. So it won't touch 0, it'll just approach 0. And that's why we're going to use the limit. Then the limit as x approaches infinity, as x gets really big, what happens to my function? My function gets really big. So that'll be equal to infinity. Now we're going to go ahead and graph 1/2 to the x and look at the difference. So -3, -2, -1, 0, 1, 2, 3. Anything to the 0 power is 1. 1/2 to the first is a half. 1/2 squared is a fourth. 1/2 cubed is an eighth. And now when we take 1/2 to the negative first power, it's going to flip that guy over and actually make that 2. If we take 1/2 to the negative second power, it's going to flip that over and make it 2 squared. So we get 4. Same thing with the negative third power, so we'll get that to be we'll get our y value to be 8. So let's graph him. A half, a fourth, an eighth. Just like before, we're going to have an asymptote here at 0. Since there's nothing I can take 1/2 to the power of to actually get to 0. So my domain, just like before, is going to be from negative infinity to positive infinity. My range is from 0 to infinity, making sure not to include 0 and putting a parenthesis there. And my asymptote, again, is going to be at y equals 0. And my y-intercept, again, is at 0, 1. So this 4 set of things, that's going to be true for any exponential function, some base to a power. It's going to be true for all of those. When we start having transformations is when things start to get kind of messed around a little bit. So on this guy, when x approaches negative infinity, well, this time, since we're switched around, as x gets smaller and smaller and smaller, my y's actually go off to positive infinity. Sorry, Ryan just got home. All right, and as x approaches positive infinity, we're going in this direction. X gets closer and closer and closer to my asymptote. So my function will be approaching 0. Oh, I shouldn't have scratched my nose. Oh, geez. I should probably wash my hands. So now that we have those functions graphed, now we're going to look at transformations of those functions. So you might have to dig through some of those pieces of information that you knew back in Algebra 2 because we're going to need them now. So that negative out front, he is going to reflect over the x-axis. So when my negative is out front, it reflects over the x-axis. When my negative is up with my x, it reflects over the y-axis. Now remember, when something is grouped with your x like that, it's going to do the opposite of what you think it's going to do. So when you see -3, you're like, oh yeah, I'm going to go to the left 3. No, you're going to the right 3. So just a moment ago, our plain old function So that orange function, this is 2 to the x. So now we're going to go through and perform these operations. So the first thing we're supposed to do is we're supposed to reflect it over the x-axis. So let's do that. We'll reflect it over the x-axis. There we go. So now it's reflected over the x-axis. The next thing we need to do, so that means this is -2 to the x. All right. And now to take care of that right 3, I'm going to take this guy that reflected over the x-axis, and I'm going to shift every point to the right 3. I like to start with my y-intercept. It helps me keep track of everything. So I'm going to move that over to the right 3. Good deal. So this guy right here is -2 to the x -3. Now let's analyze this function. So Remember, the one that we're looking at is that blue guy. So my domain for him is from negative infinity to positive infinity, just like before. With my range, my y values start down at negative infinity. And then we have y values until right here at my asymptote at 0. So since there's an asymptote there, I need to have a parenthesis on it. I'm not including 0. And I just said I have my asymptote at y equals 0. Now, I did have a point here at negative 3 1/8. So that got reflected over. So now this guy's at negative 1/8. And then he got shifted over 3. So now he's chilling there being our y-intercept. So our y-intercept is going to be at 0, negative 1/8. Good deal. Then as x approaches negative infinity, so when x gets smaller and smaller, it gets closer to my x-axis right here. So that's going to be equal to 0. And then over here, as x gets bigger, y gets really, really, really negative. So that's going to go to negative infinity. So then let's take a look at this guy. So like I mentioned just a minute ago, this negative up with the x will actually reflect it over the y-axis. And then this 4 is not included in with my x. It's outside of that. So that means it's going to move it vertically, and it's also going to act the way you would expect it to. So for negative 4, that means I'm going to shift it down 4. So let's think of that original function that we had earlier. We'll graph him out real quick. 1/8, 1/4, 1, 2, 4, 8. Okay, so now we're reflecting this over the y-axis. So remember that the piece that is on your line of reflection, that doesn't move. So my y-intercept is going to stay my y-intercept. Then it was 1/2, 1/4, 1/8. All right, there we go. So that guy is 2 to the negative x. Okay. So now, for this last guy, we're supposed to shift all of my points down 4. So I'm going to take this blue graph and shift every point down 4. Oopsies. 1, 2, 3, 4. All right, so since we shifted down 4, that asymptote that was at 0 also got shifted down 4. So now he is living down here at x equals negative 4. I'm sorry, y equals negative 4. My domain is still going to be from negative infinity to positive infinity. My range, the farthest down that my y's go, is at negative 4, and I don't touch it, so I need a parenthesis on there. And then it goes off to positive infinity. Oops. I put my asymptote where my y-intercept is. There we go. Okay, so now my y-intercept, it was up here at 1. Then it got shifted down 4, which means now it's chilling at negative 3. So my y-intercept is at 0, negative 3. As x approaches negative infinity, my graph gets really, really big, really, really fast. So I'll be going to positive infinity. And as x approaches negative infinity, so over here, it's approaching that asymptote, so that's at negative 4. Okay, so now that we kind of see how that looks in a graphical sort of way, let's look at kind of trying to see it in our heads. So without a calculator, let's find the following based on what we know about x to the 1/2 or 1/2 to the x power. So if I have 1/2 to the x plus 4, that's going to take that graph that's going like this and shift it up 4, right? So usually I would have been, when x approaches negative infinity, my function would have been approaching 0 because that's where my asymptote is. Since I'm shifted up, now my asymptote is up here at 4. So when x approaches negative infinity, what is my function approaching? 4. And then hang on, let's go back and look at this for a second. Haha, there we go. All right, so when I get shifted up 4, well, is that up 4 going to matter to that 1 or to that infinity that I had before? No. If I shift him up, I'm still going to go to infinity. And then instead of going to 0 at infinity, now my asymptote got shifted up 4. So now I'll be at 4. Thank you for dealing with my flub. I appreciate you. Okay. Now on this next one, now it's going to reflect around. So now it's going up like a regular exponential function, where as x gets really small, my function gets closer to the asymptote. So in that case, as x approaches negative infinity, that is where I'm getting closer to my asymptote. And now my asymptote is at negative 3. So that will be negative 3 right there. Over here, as x approaches infinity, so we talked about how it reflected over, so now it's going like a exponential growth. So when x goes to infinity, my function is getting really, really big. So that'll approach infinity as well. Okay, here we go. So, applications of exponential functions, who cares, right? So, first of all, something you need to know about is e. E is called the natural base. It was discovered by Leonard Euler. There are about 4 different ways to find the value of e, and it's really, really interesting. So if you have some extra time on you and you're curious about it, go ahead and look into Numberphile. They have, it's a YouTube channel. They have a video on e, and it's really, really good. So e we love to use in calculus because it's its own rate of change and all those sorts of things. So we love it, period. Anyways, so one of the ways that we use exponential functions, or that people love to apply them to, are compound interest. So if we have compound interest that's compounded yearly, biannually, quarterly, monthly, daily, etc., we're going to use this top formula right here. So the A stands for the amount in the account, or the account balance, I guess. P is the principal. Principal is the amount of money that you begin with. R is your rate. Make sure you input it in your function as a decimal. Don't leave it as a percent. And then both of these are n's. That's the number of times per year the money is compounded. So if it compounds yearly, n is 1. If it compounds monthly, n is 12. If it compounds quarterly, n is 4. So on and so forth. And then t is time, however long we are allowing that to compound. They then went and found, let's see if I start compounding my interest more and more often, what does that look like? That's how we came up with E. So when we compound continuously, we're going to use this formula instead. A is still the account balance. P is still the principal. Notice it's principal PLE, not PAL. So it's a different principal. R is still a rate as a decimal. T is still time. So here we go. Let's try a couple. So Aya has a savings account. She deposits $500 that she got for graduation. If the account has an interest rate of 0.5% compounding quarterly, how much will be in the account after 5 years? So I have to use that first formula that they gave me. A equals P times 1 plus R over N to the NT power. So for A, I don't know what the account balance is going to be, so I'll just leave that there. Principal is how much I began with, and Aya put 500 in her account. And then I'll have 1 plus. So for that rate, I have 0.5%, but I need to make sure that I rewrite that as a decimal. So I'm going to have to stick 5 zeros in front of it, and I'll have 0.005 for that interest rate. And then n is the number of times per year that it's compounded. It's compounded quarterly, so quarterly means that we're going to do that 4 times. Put a 4 on the bottom. Take that to the 4 times. And we want to know how much is in there after 5 years. So I'm going to multiply that by 5. And then we'll put that into our account or into our calculator. And you should end up with $512.64. So I want to have a conversation about actually not rounding. So what you need to do with problems that involve financials like this is you need to truncate. What truncate means is just stop writing. You're not going to look at the number afterwards to see if you go up or down, because in any financial institution, they will keep that fraction of a penny. They're not going to round it up for you. So on all of your answers, just truncate. Stop writing. We don't want to round that last one. Cool. Another one. So Raul opened a savings account and deposited $2,000. The account earns 1.3% interest compounded continuously. If he wants to buy a car in 4 years with the money, how much will he have to spend? So this time we're compounding continuously, so that means we have to use PERT. All right, so I don't know how much will be in the account at the end, so I just have to leave that as A. I started with 2,000, that's how much he put in. E. My rate is 1.3%, so that means I have 0.013 for that as a decimal. Times, then we want to know how much will he have left after 4 years, so we need to multiply that by 4. So then we'd pop that into our calculator, and we would end up with $2,106.75. Okay, so last thing, because honestly, you can't do exponential functions while you're hiding from your like society during a pandemic and not talk about it. So we're just gonna real quickly have a conversation about why everybody's trying to stay home. So coronavirus originated from a person eating a bat, right? Cool. So That infected the person. Each infected person then infects 2 others. Now we want to write a model for the situation. How many people are infected after 30 days? So let's think about this. We talked about earlier how exponential functions are a times b to the x. A was the initial value, and b was the growth or decay factor. Oh, hi, kitten. So this all began, honey, okay. This all began because of one guy. So my initial value is 1 for one dude. Times. And then the growth factor is, Peanut, get out of here. The growth factor is how fast it grows with, infecting other people. So each person infects 2 others, so that means B is going to be 2. And then that's to the x power. So if we want to, to the t power, because we're talking about time. Yikes. All right, so we want to know how many people are infected after 30 days. So I'm going to put in f of 30. So let's say 2 to the 30. All right, look how many people this is. Look at all those people. There's 1,000, there's million, there's billion. Over 1 billion people will be infected in 30 days if nothing is done. So if you're wondering why you are told to stay at home all the time, it's because we don't want all of those people getting sick at once. We want our healthcare system to be able to handle it. So, all right. Hope all of that sunk in all right. We will practice this tomorrow. So have a great day. Bye, guys.